So, so far have been talking about the left-hand side of this so-called fundamental commutative diagram. So if you have representations, I guess in the characteristic category, you can localize them onto D modules on Bungie by some procedure. And basically what I want to explain is what the analog of this operation is on the spectral side. And it will be something pretty simple. But I do want to review just a little bit what objects involved are. So yesterday we mentioned this, or proved in some way, this fundamental local equivalence, which identifies a Kacan-Lucia category with incoherent sheaves on a certain space. So this space has to do with Rupert. So here's the review, the call. So the whole talk I'm going to fix the point X. And then in your head, we should just imagine that X can be allowed to vary over the grand space, blah, 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 and all this formalism works. Okay, so we have the permitted object, the space of overs on the puncture disk. This is called morphic. This is overs on the puncture disk. And this space is a very simple space. So, for example, Dima explained that for GL3, so text with GL3, you can just write down overs as connections, and every over kind of has a canonical form. Looks like this. So it's B plus, well, some matrix, A1, A2, A3. Then you have this lower, this lower thing. And what are these AIs? Well, so A1 is a Laurent series on the disk. It's a Laurent series, really. A2 is another Laurent series, but actually the Laurent differential. And A3, your canonical. So that's just the space of overs on the puncture disk when the group is GL3. And let's just note that it's basically a vector space. It's like an infinite dimensional vector space. It has both a pro-direction and an indirection. So it's really a union of kind of power series type vector spaces, and each power series type vector space is an inverse limit of 5-dimensional vector space. So in general, the space of overs basically has the same shape, there just might be more of the A's. So equivalent, let's say u less than or equal to n, this means that I bound the order of poles by n, and e to the n is the inverse limit of, if I just disregard higher order terms. So that's what this space looks like. That's all there is. Now, so okay, whatever over is, there is an underlying G-check local system. So the space of meromorphic overs, you can just forget underlying local system. And you can impose the condition that the underlying local system extends to the non-puncture disk. So if you look at local systems which are regular, so non-puncture disk, this fiber product is what we denoted meromorphic, monotone created. That was the definition. Okay. So that's kind of the basic local object of things. So now what I have to explain to you is how to get from this local thing to the global thing, the space of local systems on the whole curve.
Why is A2 and B?
Yeah, A1, A2, and A3 are all just what I'm saying.
I mean, sure, just like on the puncture disk, it's like, I mean, what?
I mean, otherwise it's complicated. Or
Well, but there's a twist by this omega. Okay. Okay, on a punctured disk, you can just okay.
I'm not choosing coordinates, I'm not doing anything weird like that. That's honestly,
Well, okay. I change. Oh. So A, I'm not like super confident because I'm bad at coordinates, and B, it's not perfect. So maybe it's okay if you just
okay, I understand what you're saying.
But I think I was correct. So okay.
Since that's good, yeah.
Okay. So yeah, I checked this at like 2 a.m. last night, so it could have been wrong. Okay, so
I think there's sort of a dt divided by dt. So there was one dt you were divided by the place of the bundle and then
yeah, okay. All I really need is this phenomenon. Okay. So right, so how do I relate this local thing to the global thing? So I want to define functor. It will be called Poincaré star. That will. It's going to go from in total of meromorphic, sorry, monodromy free filters to the info of global local system. Okay. Local system and global. That's really all I want to explain it at first pass. What is this functor? And then you can be happy, and then I'll make comments about more things we know about this functor. So maybe the way such a functor can possibly arise is, well, some relation between this local space of Hilberts and the global space of local systems. So we have the following correspondence. So on the one hand, I can consider, let me just ignore this monodromy free condition for the moment. You can just consider Hilberts on the punctured disk. I can also consider Hilberts on the global curve of punctured at my point x. So I will call this Hilberts monomorphic global. So this is the space of Hilberts on capital X minus lowercase x. Hilberts. So any such thing, I can just restrict to the punctured disk. Get local information, and I can also forget to the underlying local system, which will only be defined away from the pump. So I'll get local system, but meromorphic, and I divide global property. This is speed check. Global. X. This is the correspondence you can write down without any thought. And now note that everything here lives over meromorphic local systems on the punctured disk. Local systems on the punctured disk. That's the base over which this diagram, the over this diagram over local systems. Okay, and now it's clear what to do. I should just base change to the locus of regular local systems. Local systems on the whole disk. Base change. One locus regular. Two locus meromorphic. Okay, so let's see what we get. Yes. So there's 3 terms. Let's complete it. So on the far left, I'm looking at Hilberts on the punctured disk, whose underlying local system has been extended to the non-punctured disk. So this, by definition, is monodromy free Hilberts. On the right-hand side, I'm looking at local systems on the punctured disk, equipped with an extension of, well, its restriction, sorry, local system of the punctured curve, whose restriction to the punctured disk has been fully extended to the non-punctured disk. So that's just the local system on the entire curve. Then in the middle, I'm looking at, well, overs on the global punctured curve, which are monodromy free at this point. And no notation for this has existed yet, so now I have to make up a notation, or tell me what the notation is. Monodromy free. This is just by definition the base change of meromorphic global alongside. Okay. So now I've created a correspondence between where we want to start and where we want to end, and now you know what to do. And this is F. You call this R. You call this F monodromy. So definition. So Poincaré star step. So well, you just pull push. So first you pull back, and then you do pull. Okay, so that is the definition. But something actually needs to be justified for this to be a correct definition. And the reason is because of this expression. So I'm trying to do star pullback on an int-code category, and this requires justification. So this functor does not usually, or may or may not exist. Okay, so I will say something about why this upper star exists. But before doing this, maybe let me just point out some features of this functor.
So,
Yes.
do you have an indication for why we want to use upper star and not upper strip?
In the spectrum or the faculty different, but not in this.
Yeah.
The country is in the coast time.
So let me let's I think
Even if what you think is like the global thing, again, not like part of it. More the global thing goes like most close thing coordination planning.
well we'll see when I explain.
Yeah, I figured it's like the street thing with the plan.
Yeah, so okay, let's ignore this for the moment and then we'll like actually look at what's happened. Very concrete terms, don't worry. Okay. So maybe the thing I want to observe is that I paint this diagram by base change along this map. So because we did base change along the map from versus G, right? Versus G meromorphic. This functor will just automatically be linear for the action of the spectral vector category. Linear over I guess I forgot what the notation is, so it's like it's both right. Now, another thing to mention is that, okay, maybe just for fun, although okay, maybe use later, is that for any category acted on by this guy, we have the notion of being tempered. And it was explained yesterday that the Cauchy-Leuschner category is tempered. So if you believe in the FLE, then the right-hand side is also tempered, although that's a really overkill way to prove it. But it is true. So one can show directly. It's not like a. Okay, don't use the FLE to do this directly. That in post are. Looks this you check monodromy free. sorry, this check 1 over 3 is tempered. And for this reason, when I apply any functor which is linear for the Satake category, I'll end up in the tempered subcategory as the target. This implies that Poincaré Spectral lands in the tempered subcategory of encroglyphs. So tempered. And the general notion term. Yes. So there's this intco. So this is okay. It's a groupoid because it's convolution. So there's a convolution monodal structure in this intco. You could do the same with qco, and there's always this functor from intco to qco, an extension of code topologically embedding into qco. And that functor is a monodal quotient. So you can ask that the action of intco factors through qco. That's what tempered is. Okay. So yeah, so the source, okay, it requires a proof, but it is true that the source category is tempered to begin with. So whatever you do using something linear over this category, you'll get something which is also tempered. And the tempered part of encoluxis, I guess Yoki this okay. It was stated by Yoki. This is nothing but just classical. Okay, so any questions about this before I okay, great. So now let me try to say something about this star pullback. So here's the warning. So even if I just have a map of finite type schemes, so in the usual theory of encode for finite type schemes, there's always a star push forward, and you can ask for this star push forward to emit a left adjoint, which you would call star pullback. And it's just not true in general that this star pullback actually exists. So the functor star X well, emit aspirational left adjoint is called. But there's some cases when it does. So, okay, let me give a negative example. So, CG, if I take point mapping into point times point over K1, this has no pullback. This is just to convince you that it's not really like you shouldn't imagine that F is like really pathological if this star pullback doesn't exist. Even for something simple like this.
Product over what? A1.
Point times point over A1. Yeah. But there's some conditions under which the star pullback exists. So e.g. the path is, let's say, quasi smooth. Sorry, this is. And in general, the criterion is that F should have finite for MVT. Well, okay.
This case is like We start with working a sheet, I just literally pull it back and now it's slowly down below and it's going to.
Yes.
Don't reach this.
I won't. But like someone might want to see because it has. Right. The point is that this criterion is really something about F as a morphism. It's really a relative, more or less a relative property of F, that this morphism is nice enough. And so if I want this map F monoidally free to this star pullback, well, probably it suffices to check it for the map that it was obtained via base trip. Sorry, F. We don't look that. And okay, that's how you do proof. So let me now just look at this map. What's the nature of this map? So Y. I don't think. Okay, so I think here's the time for me to remind you, like, what exactly is this enclosed star? So enclosed star. So in this example, okay, so I just erased it, but this space, I mean, is really like a vector space. So really, so first I write it as a union of schemes, so it's element of enclosed star, where I bound the order of the pole, let's say like n. And for each of these infinite dimensional things, I reduce the finite dimensional case by pulling back from, well, finite dimensional coefficients. I guess I'll write it in a way that Ema wrote it, so pulling it, this is pull back. So it's the ordinary. This is really just pull back along in the projected map of vector spaces. Okay, so if I want this F number circuits, I just have to tell you what it does on all of these generators. So just you take something on this quotient, you pull it back to the subspace and you include it, and it is to tell you how to compute F number star. And well, for this, I had better give some sense of what this source base looks like. So here now. So global overs on the curve, the final way in the curve. And as in the local series, this is also something super explicit. You can just write down connect. So overs. Now okay, global. So for B reveal B. Okay. It's E plus. And just write the same thing. So A1, 2, 3, 1, 0, 0, 0, 1, 0. So previously these A's were Laurent series because I was being defined on puncture disk. Now I'm on a global curve with functions, so they should be, well, just functions on the global curve. But with poles at this point. So AI X and who knows? So very confusing. But okay, so basically they're just okay. Okay, on a puncture with Jesus, one of this. Knows what it is. Okay. What's the nature of this vector space? So previously we had an infinite dimensional vector space, but kind of was law of Laurent series nature, so it's infinite in two directions. This kind of vector space is only infinite in one direction. So if I bound the order of the pole, I get a finite dimensional vector space, and I just pick the union. So this really looks like the full limit of this finite dimensional vector space. And so here's maybe the diagram. So
But,
so inside my space of overs on the pointer disk, I can just bound the order of the pole of the connection, some vector space. And kind of my generators are just pushed forward from here of something pulled back from finite dimensional. And I want to take the star pullback. So now let's just believe that whatever the star pullback is, it's supposed to satisfy base change against push forward along the closed inversion. Because I know star at base. So if I look at global overs whose restriction to this to the bounded order of whole, well, okay, that's just one of these finite dimensional spaces. L less than or equal to n. So I really just need to know how do I take star pullback along this map. And the star pull along that's an equal n. N minus m. Okay, so like this is a vector space. This is a vector space. I just have a linear map. Certainly, it's quasi-smooth. Actually, the existence of this pullback is not so not for any like really. Okay. So now now we should probably talk about this part of the diagram. Say something about that. So something Lin explained was that we know how to compute. So do localization and then just do the vacuum Whittaker coefficient. That produces some vector space, and there's some explicit expression for this vector space in terms of factorization from all of it. Some like purely local, well, kind of purely local description of this function. And now we want to see the same kind of phenomenon on the Langlands full side, and then tomorrow we'll kind of try to match the two descriptions. Here's the video. So if I start drifting to star, I'm monitoring the papers, and I apply my newly defined Poincaré star. Okay, so it turns out that there's like more fancy ways of probing incoherent trees on Moses tree than just taking global sections. So there'll be some more fancy things you can do. For the moment, let me just consider global sections. Just get about it. And this is supposed to have a description, well, some factorization volume type description, and that you know, provide in the previous few hours. You could guess the answer, like you're supposed to insert the vacuum, integrate, something like this. And here's how it just in this example works out. So I'm looking at monogeometry overs on the puncture disk around my point x. Secretly, there's the x in there, so it's generates, but it was chosen at the beginning at the top. And we know that these things can be encoded as factorization modules. So I'm not so I can just include them as factorization modules for, well, I guess the algebra function unmeasurable. So now this is something that lives over this branch of x space, and the fiber at just the spectral point x is kind of global sections of the original diagram. And then we can just, okay, and note, and let me just recall that this functor has the nature of inserting the vacuum everywhere else. So we saw that yesterday, and now today there's some like formal mechanism that just always does this kind of procedure for you, but that's what it does. And then you can just take global sections over Rod space. So that was called C. The claim is that this diagram proves.
Kevin, are you going to kind of make contact with what Lynn was doing, or should do you want me to comment on that?
Well, which part of what then was proof?
The second part.
This
So like to turn, like to reduce this diagram for a diagram with only wax units.
no,
Can I do it?
you can, but for pedagogical reasons, I don't want to say these like words like lax. So
Okay.
I think like if you understood the previous talk, you could insert them yourself, and if you didn't, then
Okay.
I'll just traumatize you again. So like
Let me tell you, another way to where this functor or the other vacuums take the local sections and then improve the version.
These are the words. But
yes, but like that's exactly how this left functor was defined yesterday. It was you have your incoherent sheet, you can just like take its global sections, and then we had this procedure which inserted the vacuum everywhere else. It was by hand constructed yesterday, and then you just take a look like the shape of that. Well. Okay, no, I mean you can make more comments if you want.
it's okay.
Okay. Great. Okay, so here is how to prove this. So basically, there's like the one fact I know about factorization, which is, well, we'll see. Proof by example. In the previous talk, we also had proof by example. This will be the same, proof by example. Let's just see that this diagram commutes on a particular object. Let's plug in, so okay, let's plug in. Well, what else? The vacuum. So, we don't know where to start. Right, this is maybe if this was actually false. Ah, sorry, it's something illegal. I should do something. So this is monodromy filters. I can go to meromorphic filters. Click forward. Okay, this was the thing which I related to factorization model. It's not that. So where we are. So let's just see what happens by plugging this up. Go in both directions. So if I go along the upper direction, kind of the thing that doesn't involve any factorization, what am I doing? So I'm looking at the regular groupers. So on this, then I'm taking a push forward to monodromy freeovers. That was the inclusion denoted I plus. Then I do this Poincaré functor. Poincaré functor was, well, pull back to global groupers, which were monodromy free at my point. And then push forward to lotuses and take global sections. So I can just take global sections. Okay, push forward, pull back in the global sections. Now, what is what is this fiber product? It's overs on the punctured curve whose restriction to which happens to be which is monodromy free, and then when you restrict it to the punctured disk, that monodromy free over actually now is being extended to just a regular over. So really, I'm just looking at overs on the global. So I'm starting with O here, I'm pulling back to just global overs and then taking global sections. I just get functions on global overs. So upper circuit. Functions is yes. Functions on global overs. What is the lower circuit? So I started with the vacuum, and then I view it as a factorization logic for itself, and then take factorization homology. Or sorry, factorization homology, that's what it's called. And then I get some vector space. And one thing that what is called Ron magic does for you is that it tells you that if you view a factorization algebra, a unit of factorization algebra, the module for itself, if you take factorization homology, you could have just taken factorization homology of the original algebra. With the lower circuit is factorization homology of this regular. And the space of regular overs, because of this very explicit quote, this explicit type of description with connections, it was an affine D scheme over X, whose global sections or horizontal global sections is the space of global overs. So this fits exactly into the paradigm that Nick explained. So this space is an affine scheme whose algebra functions is this algebra. So Nick once this you check global is the affine scheme with confidence. It really just comes down to factorization homology of something commutative. Now there's one problem. So this proof by example, which is I didn't give enough examples. So this object doesn't generate the whole category. And that's definitely a problem. Let me just maybe just indicate a little vaguely how to get around this problem. But I don't want to give more detail. And the way you get around this problem is you say, okay, so we have affine D scheme over X. So I actually want to access, all horizontal loops into Y, not just horizontal arcs, right? So this previous calculation kind of does it for horizontal arcs, but not for all horizontal loops. Something you can do is, so it is possible. Something you can do is you can modify Y at your particular point. Turns out this is possible. And so you can write Y, let's just say define so yi is yi for receiving that to line. So modifying y and just at the point. So everywhere else is actually the same affine D scheme at Y. At this point, something very funny will happen. And you can bring these yi's so that when I take horizontal arcs into yi, these guys will actually exhaust horizontal loops into y. So, horizontal loops into y. This is what allows you to kind of reduce to this kind of vacuum calculation. Okay, and I think that's all I wanted to say.
But you didn't say about gamma spec.
Oh, sorry. Yes. Okay. I should define this, although it has no logical connection to anything else in your talk. But perfect. But this only takes like 1 minute.
So we should take the applause back.
Yeah. Okay. So what is this gamma spec? So previously there was a functor in the other direction called log spec.
No, Kevin, maybe just before you run, I have one request from you collectively first. So, if you could just say it somewhere on the board, there's this bottom arrow in the diagram that you're looking at right now.
This one.
So, that's sort of the two of them together.
This one.
Amazing, yes.
Yes.
But that's like, that has its own geometric interpretation.
Yes, that's right. Yes, probably. Okay, I agree. So because I made this mistake of forgetting to insert this, like I don't know why I made this. Okay, so yeah, this arrow. Okay, maybe I should say that. So in the proof, we saw that when you do this composition, you're really just pushing forward to just all meromorphic copers and then, well, doing some pullback and global set. So really, let me say the assertion for general affine DC. First. So on the one hand, so the version of the lower arrow in general would be obtaining a factorization model by inserting the vacuum everywhere else. And then you just take factorization model. Yeah. And what this is doing very concretely, so this is some kind of local procedure, and what the local to global compatibility you get is that this is the same. And pull back the horizontal sections on the control there, then take the open. That. This is kind of this theorem is really a formal consequence of this for a particular formal plot. That's good. Okay, yes, so thank you very much. So and okay, now let me tell you what this gamma spec is. So what was log spec? It was a way of just tautologically producing objects of incolluxus, or maybe quasi-corporate. This tautological procedure was encoded by the following diagram. So we have UGFL. And Luxus maps to this. So at any point of the Ron space in the local system, we can just evaluate at those points. Let me call that. This. Yeah. And the definition of log spec was, well, okay, so you have something here, you pull it back, and then you push forward. So the push forward, maybe you module, you push forward. Gamma spec is, okay, just go in the other direction. Is by definition. So, and so note that this is the right front of the closed event. That's another way to think about it. And you want me to say that there's wolf?
No.
Okay, okay, end of the pause.
We have